Hi, it's Mr. Anderson, and this is AP Physics Essentials video 85. It's on thermodynamics and PV diagrams, or pressure volume diagrams. And this is a picture of a fire piston. You can put some tinder, like cotton, in the bottom of a fire piston. You can slam your hand down on it, and since heat doesn't have time to escape from that piston, we heat it up and the thing starts on fire. And natives have known this for a long time. This is a native fire starter. You put some tinder on the inside, you slam it down, and then it starts a fire. And so a part of the conservation of energy is the first law of thermodynamics. Energy can neither be created nor destroyed. But we're going to study how this applies in a typical idealized gas, in a piston like this. And so our equation is delta U, so that's the change in internal energy, is equal to Q plus W. Q is going to be heat and W is going to be work. And so we can add energy to this system, this internal energy, by heating it up, or we can apply a force over a given distance to it. We can do work on it. And so what we're looking at is how energy can be transferred from the surroundings into the system and back again. Now we're not going to lose any energy. Remember, the energy is going to be conserved. And a good way to measure this using a piston is to graph the pressure and the volume over time. And so we're going to start with the piston kind of relaxed, and we're going to have a really high volume. So we've got a large volume here, but it's going to be a relatively low pressure. And then I'm going to compress that piston. So the surroundings are going to do work on the system. And as they do that, you can see we have an increase in the pressure inside. Now we did it slow enough that we're allowing that temperature to stay constant throughout that whole process. And so what's neat about a pressure volume diagram is the area under that curve is going to be the amount of work that we do. Now a common mistake in physics is to figure out who's doing the work. Is it the system or is it the surroundings? And so in any piston like this, the area under the curve is the work being done by the gas. And so you can see that we're going from right to left, and so this is negative work. And so what's work being done by the gas? It's negative work. Well, if it's negative work of the gas, that means it's positive work of the surroundings. We're adding work on the system, and so we're increasing the amount of internal energy on the inside. This would be an isothermal process, since we're keeping this temperature the same. Now in physics 1 and 2, you don't have to do calculations, you just have to know qualitatively what's going on. But we could have a different process that we'll model here. It could be isovolumetric. We could lock the volume of that piston, and we could just add energy through heat. We could have isobaric when we keep the pressure the same, or in the fire piston we can do adiabatic cooling or heating. So that's when we're doing it so quickly that we're not allowing heat to kind of move in and out. And so let's start with a little simulation here. This is a PHET simulation. We've got the gas molecules on the inside. We can add heat right here, and then we can push back and forth on the piston on this side, so we can do work. We can apply a force for a given distance. And so let's watch what happens when we run the simulation. The energy is in the molecules on the inside. What happens as I add temperature to it? I'm increasing their speed, and so I'm increasing their energy. Energy of the system increases. If I cool it down, energy of the system decreases. How else could I add energy? Remember, it's W, it's work. So we could push in on it. What's happening to the pressure and therefore the energy on the inside? It's increasing, and now that total internal energy is decreasing over time. And so it's nice to be able to use a simulation, but the two things that we can measure are the volume and the pressure. And so if we just keep track of the volume and the pressure over time, we can figure out what kind of a process is going on. And so this is a PV diagram. And so let's start with an isobaric process. In an isobaric process, we're going to keep the pressure the same, but we're going to be able to change the volume over time. And so a way to do that is allow this piston to move in and out. And so we can change the temperature. What's going to stay the same? It's going to be the same pressure on the inside. So that piston's going to move back and forth, but we can add energy into the system or we can pull energy out. Since it's free to move, the pressure is going to stay the same. And so if you see on a PV diagram this horizontal line, then you know it's isobaric. What else could we do? We could do isovolumetric. What does that mean? We're going to keep the volume the same. You can see the volume is always the same, so it's just going to move back and forth on here. We're going to increase or decrease the pressure. And so what would that look like? Using our piston, we're going to lock it in place. Now we can add temperature. We could pull that temperature out. We could also have isothermal. Isothermal is always going to look a curve like this. This would be an isothermal curve. And so how do we do that with a piston? Well, we'll use something like a heat sink where we can keep the same temperature throughout that whole process. And then finally, we could do adiabatic. That's where we either pull it out or move it in really, really quickly and so fast that we can't lose temperature to the surroundings, and you're going to get a curve that looks something like that. Okay, so let's kind of model those using this PHET simulation. And so let me kind of get this thing going. There we go. And so now what we're going to do is we're going to keep the volume constant. So we've locked it in place. How are we going to energy into the system? We could add heat. As we add heat, we increase temperature, pressure is going to go up. Let's say we add ice on the bottom. We're going to pull energy out of it. Heat's going to flow from the system to the surroundings, and the pressure is going to decrease. What's staying the same that whole time? The volume is going to stay the same. For the second one, let's keep the temperature constant now. So we've got a constant temperature. So you can see that I can't even change my heat controls here. So how am I going to get energy into or out of the system? It has to be through work. So if I apply a force from the outside, what's happening to the pressure on the inside? It's going up. If I do negative work from the outside, what's going to happen to the pressure? Pressure is going to drop off. And so we're going to get that nice curve on a PV diagram. And then finally, we can look at an isobaric process. In an isobaric, we're going to keep that pressure the same. What does that mean? This piston can simply move back and forth. It's going to be the same pressure exerted by the gas. If we cool it down, those molecules move slower. The piston's simply going to move in. If we were to add temperature to it, as we increase temperature, that we're adding temperature or heat into the system, what's going to happen? Those molecules are going to move quickly, but since the pressure remains the same, the piston's going to move out. And so what would the PV diagram look like in an isobaric process? Since that piston can move back and forth, the pressure is always going to remain the same. And so the volume is going to change over time. And so remember, the area under a pressure volume diagram is going to be the amount of work that we do. And so since we are taking a large volume and moving to a small volume, the work is going to be in that direction. And so we'd be doing negative work. Now remember, that's negative work of the gas itself, what's inside the piston. So what's the positive work? That's from outside. So that's going to be the work of the surroundings. And so did you learn to figure out how internal energy in a system can change? It's really only two things. We could add heat or Q, or we could do work. Do you know, looking at a PV diagram, which of the 3 or 4 processes this is? So this would be isobaric, this would be isovolumetric, this would be isothermal, and this is going to be adiabatic. And then finally, could you find the area under the curve? And if you know the area under the curve, could you figure out how much work is being done by the gas? Because that's going to be what's under the curve. I hope so, and I hope that was helpful.